Alright, let's do the next problem. Apologies, I looked at my videos before and it seems like I'm not as chirpy as I am usually. I am a really happy person. Those videos weren't done at the earliest of time, so I'll try to stay a bit more snappy this time. So in this problem, we have some teenagers that built an electric car. It can get up to a speed of 30 meters per second. And if we say that if it takes 8 seconds to get to that max speed from 18 meters per second, we need to find out the magnitude of its acceleration. So first off, obviously our direction, let's put that in red. Our direction in the positive direction is the direction of the car. Oh wow. Oh, Mr. Coombe cannot write today. Sorry about that. Of the car. Okay, so if we know that the direction of the car is a positive direction, all our values are also going to be positive again. So let's take out all the values that we know. So we know that it's going to speed up from an initial velocity of 18 meters per second, and it's going to get to a max velocity. So our final velocity, being its maximum velocity, is 30 meters per second. And we want to find out, and this, we also have time. So we also have time. Let me put time as in magenta. We also have our time. It takes them 8 seconds to accelerate to their max speed. So we want to find out our acceleration. Acceleration is, we don't know, and it's going to have the units meters per second per second. This problem is pretty intuitive, so let's have a look at which formula we use. So we want to find out acceleration. We have v, u, and we also have t. So the equation that we use is v equals u plus a t. Let's plug in our values. Our final velocity, let's put it in yellow, our final velocity is 30 meters per second, which equals our initial velocity, let's put that in blue, it's 18 meters per second, plus our acceleration, let's put our acceleration, in green, our acceleration multiplied by our time. What color is our time? Our time is in time is in purple, right? Our time is 8 seconds. Beautiful. So in order to get our A out, if we take away 18 from both sides, so it'll be 30 minus 18, I believe is 12. So let's say on this side, and we'll put that in blue. So we have 12, well, in white apparently, 12 meters per second equals our A, green A, times our 8 seconds. 8 seconds. So in order to get our acceleration, we obviously divide both sides by 8 seconds, so we have 12 meters per second, and let me just undo those, and I'm going to separate my units again. 12 meters per second divided by our time, which is 8 seconds. Okay, so this, if this is meters per second, if that's -1, that's going to go down here. So this will just become seconds by second, so it'll become seconds squared here, but 2 seconds here. And 12 divided by 8 is 1.5. So our final acceleration should be 1.5, and then here we still have meters, so meters. Now here seconds, seconds to negative 1 goes down here, that becomes squared, so seconds to the negative 2. So that is our final velocity. The other thing I wanted to discuss in this particular video is, let's look at this graphically. If we look at this graphically, it's something a little bit different to think about. Let's say that, let's do a velocity versus time graph. So if we graph, wow, that's horrible. We graph it, that's better. If in our x-axis is change in time, and that'll be in seconds, and if we do our y-axis, whoa, Mr. Coombe cannot write very neatly. I will leave that, that's fine. And our y-axis is our velocity, okay, it's our velocity, and that'll be in meters per second. And let's say at time 0, our velocity, what was that time? At time 0, our velocity, let's say that this here is our max velocity, that's 30 meters per second. So if this is 15 here, our initial velocity is going to be somewhere there, which is 18 meters per second. And then we know after 8 seconds, it will reach its maximum velocity in that 8 seconds. So if we join up those two lines, we can see, and it should be a straight line, and we can see here that the acceleration, just the rate at which this speed changes, is going to be the gradient of this line, which is 1.5. So if you have a look, if you take the difference between 30 and 30, our final velocity, which is 30 meters per second, and our initial velocity was 18, so the difference between them is 12 meters per second. So if that's our rise, and then we divide that by how long it took, so our run, so let me just put that in, so our rise, okay, our rise was 12 meters per second, and our run was 8 seconds. So if we divide our rise by our run, we get the gradient, which is our acceleration. So for every second that passes by, the velocity gets faster by 1.5 meters per second that passes by. Now another thing that's quite interesting that I want to actually show you guys, and it's not part of the question, but how do we find the displacement now? Just using the graph. We can actually do this using the graph. And I can tell you that using the graph, to get the displacement, you actually just calculate the area and under this curve. So all of this, and I'm going to do it in 2 colors. Do all of that because it's a bit of a different shape. It's a bit different. I believe it's a rhomboid, if I'm not mistaken. How do we calculate the entire area of that? So the way we calculate the entire area of this shape using some geometry is we split it into 2 sections. So we have the area of a triangle, and we have a rectangle. Now if you think about it this way, it sort of makes sense. So if for example, if we had started at initial velocity, let me write that in, our initial velocity was 18 meters per second. If we had kept on going for 18 meters per second over that 8 seconds, then our displacement would have been 18 times 8. So let me just get the calculator out, sorry. So that would have been 18 times 8 seconds. So in that time, so the area of this square here is 144. So in this one, if you had kept going at 18 meters per second over the 8 seconds, your displacement would have been 144 meters. But our velocity changed during that time. So let's have a look at the area of this curve. The area of this under this curve is, so to find out the area of our triangle is half our base multiplied by our height. So half of 8 is 4. 4 times 12 is 48, I believe. Let me just check that. 4 times 12 is 48. Yes, Mr. Ping was correct. Just to check, just in case. Alright, so our area under that is 48. So during that time, you would have displaced yourself an extra 48 meters because of that extra speed that you're going at. So then your total displacement is going to be 192 meters. So the total displacement is going to be 192 meters. And let's check that. So let's check it. If we have S equals ut plus half at squared, our initial velocity was 18 times 8, which is this area, plus half. Our acceleration was 1.5, and our time was 8 squared. If we do those values there, 18 times 8, which is our 144, and we have a half times 1 point, oops, so that half times 1.5 times 8 squared is 64. Okay, so you saw by the calculator that our final area is 144 plus 48, which is the same as 192 meters. So we've solved that now by looking at the area under the curve to get our displacement. So hopefully that was helpful for you to look at, not only numerically trying to figure out displacement, but also graphically in order to try to find displacement. Also acceleration you can find graphically. Right, I hope that was helpful.